The human brain is the most powerful organ in our body, yet we still don't fully understand how it works. Even with all the advances in science and technology, many brain functions remain a mystery. Why do we dream? What triggers déjà vu? How can some people remember every detail of their lives while others forget moments instantly? These aren't questions with clear answers. In fact, the more we learn about the brain, the more questions we seem to uncover. Some people have woken up speaking new languages after head injuries. Others can see colors when they hear sounds, a rare condition called synesthesia. Then there are cases of people living normal lives with very little brain tissue, puzzling doctors and researchers alike. These strange stories aren't just random events. They point to how much we still don't know about the brain's power and complexity. This video takes you into the fascinating world of the brain's unexplained mysteries. It's a world where logic doesn't always apply, and science is still catching up. There is something quietly astonishing sitting just behind your eyes. You carry it with you every moment of your life. It works while you are awake. It works while you sleep. It hums along in silence, keeping your thoughts flowing and your heart beating. It is your brain. It is not made of wires or metal. It is soft and silent. But it is more powerful than any machine we have ever built. Scientists call it the most complex object in the known universe. That is not an exaggeration, it is a fact. Your brain is made of about 86 billion tiny cells called neurons. These cells talk to each other using tiny pulses of electricity and chemicals. Each of these neurons can connect to thousands of others. This creates trillions of connections. These connections shift and change constantly. Even while you are watching this video, your brain is changing. That is part of the mystery. You see, we understand how to build computers. We design them, we program them, we control how they work. But we did not build our brains. We were born with them. And even after centuries of study, we do not really understand how they work. To get a sense of how little we know, think about this. There is a tiny worm called C. elegans. It is so small you need a microscope to see it. It has exactly 302 neurons in its entire body. Scientists have mapped out every connection between these neurons. They know how they are wired. But still, they cannot fully explain how this worm behaves. They cannot say exactly how it eats or crawls or reacts to light. Now think about your brain, with billions more neurons and trillions more connections. If we cannot fully explain a worm, how can we begin to explain ourselves? The truth is, we are only scratching the surface. And yet, this quiet 3-pound organ does things no supercomputer can do. It helps you fall in love. It helps you understand jokes. It lets you recognize a friend's voice over the phone. It remembers the smell of your grandmother's cooking. It can even imagine things that do not exist. And it does all of this using less power than a light bulb. Your brain runs on about 20 watts of energy. That is less than the power it takes to run a ceiling fan. Meanwhile, massive computer systems can use thousands of watts just to solve basic problems. They can beat us at chess, but they cannot understand humor, or sorrow, or kindness. That is the big picture problem. The brain is doing things we cannot replicate, and we do not know how. Now you may be wondering why this mystery should matter to you. It is a fair question. After all, your brain just works. You do not have to tell it to think. You do not have to command it to form memories. It does these things on its own. But this mystery matters more than almost anything else, because every part of your life is shaped by your brain. Every thought you have, every memory you hold, every dream you chase, these come from the silent work your brain does behind the scenes. And when the brain does not work right, everything changes. Imagine losing your memories. Imagine not recognizing your own child. Imagine feeling deep sadness every day for no reason. These are the realities of brain diseases. Alzheimer's, Parkinson's, depression, conditions that affect millions of people. Families are changed forever. Lives are lost. And right now, we do not fully know why. If we could understand how the brain works, we could find better treatments. We could stop diseases before they begin. We might even repair damaged parts of the brain. But to do that, we must first solve its deepest mysteries. And that leads us to a strange truth. The brain is studying itself. Think about that. We use our brains to try and understand our brains. It is like trying to see your own eyes without a mirror, or trying to read the outside of a book while trapped inside its pages. This creates a puzzle within a puzzle. To make it even harder, every single brain is different, not just from one person to the next, but also from one moment to the next. Your brain is always changing. When you learn something new, connections between neurons shift. When you remember something, they shift again. The brain is a moving target. As soon as scientists think they understand one part, it changes. And we are limited by our tools. Right now, we can only see tiny parts of the brain at a time. We can scan a brain. We can look at slices under a microscope, but we cannot yet watch all the billions of cells working together in real time. It is like trying to understand a movie by looking at a few still frames. Despite all this, scientists are making progress. New tools let them watch more neurons at once. New ways of looking at the brain, like MRI and optogenetics, are opening new doors. Artificial intelligence is helping them sort through huge amounts of data. Slowly, the fog is lifting, but there is still a long way to go. That is why this journey is worth taking. In this video, we will look at 10 big brain mysteries. Each one is its own universe of questions. Why do we sleep and dream? How does memory really work? Where do emotions come from? What is consciousness? Why do some brain cells get sick while others stay healthy? These questions are not just for scientists. They touch all of us. They shape how we see the world. They shape how we see ourselves. As we move through each of them, we will meet real problems and real possibilities. We will hear about ideas that might change how we think about thinking. We will explore the edges of what we know. And we will discover how much we do not know. But here's the most beautiful part of this mystery. Not knowing is okay. In fact, not knowing can be the start of something wonderful. Every mystery begins with curiosity. Every discovery begins with wonder. And the more we learn about the brain, the more wonder we find. The brain may be the most amazing computer we do not understand, but maybe that is what makes it so special. You're not just a machine, you are a person. You love, you hope, you dream. And all of that comes from the strange, silent work of your brain. By the end of this video, you will not have all the answers, but you will have new questions, better questions. And you will begin to see your brain not just as an organ, but as a mystery worth exploring. Your brain is made of living parts. Billions of them, each one so tiny that you could not see it with your eyes, but together they shape who you are. They hold your memories, they build your thoughts, they guide your movements, they make you feel joy, or sorrow, or hope. These tiny parts are called brain cells, but calling them cells sounds too simple. They are more like living machines. Each one has a job, each one plays a role. And somehow, all of them work together without anyone telling them what to do. For a long time, people believed there were just two kinds of brain cells, neurons and glial cells. That was the old story. It made sense. It sounded neat. But the truth is much messier. Let's start with neurons. These are the stars of the show. You might have seen pictures of them. They look like little trees with long branches reaching out in every direction. Neurons send messages. They fire tiny sparks to talk to each other. These sparks are like signals. They carry everything from the sound of your mother's voice to the thought that you need to buy milk. One neuron might connect to thousands of others, a whole network, like a city lit up at night, always alive with action. But neurons cannot do their jobs alone. That is where glial cells come in. For years, people thought these were just helpers. The name glia even means glue. They were seen as background workers, not important, just there to support the stars. But that idea has changed. We now know that glial cells are deeply involved in brain function. Some of them clean up waste. Some help neurons grow and repair. Others make sure the electrical signals travel smoothly. Some glial cells even talk to neurons in their own strange way. They may not steal the spotlight, but without them, neurons would fail. Now here's where things get even more interesting. There are more types of brain cells than we ever imagined. Scientists used to think we had a basic list, but with better tools, that list keeps getting longer. Some cells look like neurons but act differently. Some seem to switch roles depending on where they are. Others don't seem to fit into any known category at all. Imagine having a box of puzzle pieces, but no picture on the box. You don't know how many pieces you have. You don't know what the final image looks like. Some pieces look the same but don't fit in the same spot. That is what scientists face when they study brain cells. They're trying to build a map of the brain's building blocks, but many of the pieces are missing. Some may not have been discovered yet. Even worse, the same kind of cell can behave differently depending on where it lives. A cell in the front of the brain may act one way. The same cell in the back might act another. It's like having two identical tools, but one is used for painting and the other for surgery. That makes mapping the brain very hard. To To truly understand what the brain is made of, we need to know what kinds of cells exist, what they do, how they connect, and how they change over time. That sounds simple, but in reality, it is one of the biggest challenges in science today. The problem is not just about counting, it is about understanding. Think about this. When you go to a hardware store, you see rows of screws, nails, wires, bolts. Each one has a label, a use, a size. We understand them because we invented them, but brain cells were not made by us. They evolved over millions of years. We are still figuring out what each one does. New technologies are helping. One breakthrough is something called single-cell RNA sequencing. That's a big term, but it means this. Scientists can now study one cell at a time and look at the tiny bits of code inside it. This lets them see what the cell is doing, what genes it's turning on or off, what job it might have. This is changing everything. With this tool, researchers have found that even cells that look the same can be doing very different jobs. Some help with memory, others control movement. Some respond to light, others to sound. We are discovering more and more subtypes of cells. It's like learning that dogs and wolves and foxes are all part of a bigger family. They may look similar, but each one behaves in its own way. And then there are the mystery cells. These are the ones that don't fit into any known group. Scientists find them in brain scans and slices. They see their shapes, but they don't know what they do. Are they sending messages? Are they cleaning up? Are they waiting to be activated? No one knows yet. That's why scientists are searching for something big. They want to create a kind of periodic table for brain cells. You may remember the periodic table from school. It organizes all the elements in the universe: hydrogen, oxygen, carbon. Every piece of matter can be traced to one or more of those elements. Now imagine having something like that for the brain. A table that lists every kind of brain cell, where it lives, what it does, what happens when it goes wrong. That is the dream. If we had that table, we could unlock so many secrets. We could learn why some people get brain diseases and others don't. We could target treatments to specific cell types. We could design better medicine. We might even learn how to grow healthy brain cells to replace sick ones. Right now, scientists are building that table piece by piece. Slowly, carefully, patiently. Every new discovery brings more questions, but also more hope. And the best part is, these discoveries are happening now, not in the distant future. Labs around the world are sharing data. New projects are mapping the brain like never before. Teams of researchers are working together in ways that were impossible a decade ago. We are in the middle of a quiet revolution, one that could change how we treat mental illness, how we understand memory loss, how we help people recover from strokes, how we think about learning and emotion and thought itself. And yet, for all our progress, one thing remains true. We still do not know exactly what we are made of. Your brain holds the secrets of who you are. But to truly know yourself, we have to understand your cells. Every single one. The messengers, the helpers, the quiet ones, the strange ones, the ones we have not even named yet. The search continues, and the mystery deepens. Your brain is a miracle of nature. It holds your thoughts, your memories, your personality. It controls your body without you having to think about it. It keeps your heart beating. It tells your lungs to breathe. It stores the name of your first pet. It knows the way home. But sometimes something breaks. Slowly or suddenly, things begin to go wrong. A name you knew yesterday is gone today. A hand that moved with ease now shakes. A bright mind grows heavy and dim with sadness it cannot shake. These are the signs of brain diseases. They come in many forms. They affect millions of people. And they remain some of the hardest puzzles in all of science. What makes these diseases so strange is not just what they do, it is how they do it. They are oddly selective. They do not strike every brain cell. They go after specific ones. Take Alzheimer's disease. It does not wipe out the whole brain at once. It begins quietly in memory cells, the cells deep inside that help you remember names and places. These cells start to weaken. Then they die. Slowly, more parts of the brain are pulled in, but it all starts with those memory keepers. Parkinson's disease tells a similar story. It does not attack every neuron. It targets the ones that help you move. The ones in a small part of the brain called the substantia nigra. These cells produce dopamine, a chemical that helps control smooth motion. When these cells die, movement becomes stiff and shaky. Walking gets harder, hands tremble, faces freeze. And then there is depression. Not a passing sadness, not a bad day, but a heavy, lasting weight on the mind. Scientists believe it involves cells that control mood. These may live in areas like the prefrontal cortex or the amygdala, but we are still not sure. We do not yet fully understand which cells are involved, or why they change. That is the mystery. Diseases pick their targets. They attack some cells and leave others untouched, even when those cells sit right next to each other. Why? We can see the damage in the brain, we can scan it. We can track which areas get smaller or lose function, but we do not yet understand the why. Why do those cells die? Why do they go first? What makes them more fragile? Scientists call this the missing link, the connection between what we see and what causes it. We can follow the trail of destruction, but we cannot always find the spark that started the fire, and the timing makes it harder. Brain cells do not all die at once. They follow patterns, they break down in stages. Some live longer than others, but we cannot predict when or why the pattern begins, or when it will speed up or slow down. Two people with the same disease may get sick in very different ways. One forgets faces first, another loses their sense of time. Why? This is what makes brain diseases so hard to treat. We are not just trying to fix something broken. We are trying to fix something we do not fully understand. The medicines we have are not precise. They are like tossing paint at a canvas and hoping it lands on the right spot. Some medicines help, for some people, some of the time, but they do not always work, and they do not always work the same way for everyone. Many brain drugs were not even made on purpose. They were found by chance. A chemical meant for one problem turned out to help something else. That is how early antidepressants were found. It was an accident, a lucky one. Even when a drug works, we cannot always guide it. It spreads through the whole brain. It cannot reach just one cell type. This can lead to side effects, because cells that do not need help also get hit. It is like using a hammer when you need a scalpel. But now, something is changing. A new kind of science is taking shape. One that starts not with symptoms, but with cells. Scientists are creating detailed maps of the brain, not just what the brain looks like, but what it is made of, cell by cell. These are called cell atlases. They show how many types of brain cells exist, where they live, how they work when healthy, and how they change in disease. These maps are powerful. They help us spot the first cells to go wrong, the ones that die earliest, the ones that send out warning signals. If we can find those first weak spots, maybe we can act sooner. Maybe we can stop the disease before it spreads. The Human Cell Atlas and the Brain Initiative are big projects doing just that. They use new tools to look deeper than ever before. They study single cells, not just whole brain regions. They use genetic tools to see which cells turn on harmful processes. They use imaging to watch living brain tissue in real time. In the past, we could only guess. Now we can watch. These tools may lead to treatments that are sharper and safer. Instead of flooding the whole brain with medicine, we could one day target just the sick cells. We might be able to design treatments that only bind to certain cell types, or even use gene therapy to fix cells from the inside. This would change everything, for people with Alzheimer's, for people with Parkinson's, for people with depression, epilepsy, autism, and more. It would also help us understand the brain more deeply, because behind every disease is a story about a cell that lost its way, a message that got scrambled, a system that forgot how to balance itself. And as we study these stories, we learn more about what a healthy brain needs, what it takes to protect it, what it takes to help it heal. There is still so much we do not know, but the road ahead is clearer than it was. With each new map, each new discovery, we get closer to answers. We may not be able to stop all brain diseases yet, but we are learning how to listen more closely, to hear the first whispers of change, to understand which cells are in trouble, and to find the right way to help. Your brain is not just a collection of cells. It is a living, changing, learning part of you. When one part breaks, the whole can suffer. But if we understand the parts, we may one day heal the whole. That is the hope. That is the journey. There is a quiet world inside your head. It never sleeps. It never stops. It hums with signals every second of your life. This is the world of brain cells talking to one another. You do not feel these conversations. You do not hear them, but they are happening right now. As you watch this video, as you think, as you blink and breathe and wonder, your brain is alive with chatter. In school, we are told the basics. Brain cells or neurons talk at places called synapses. A signal travels down a neuron. At the end, it jumps across a tiny gap. The next cell receives it. This is how the brain sends messages. That is the textbook story. But the real story is much deeper, more beautiful, and still full of mystery. The brain is not just a simple switchboard. It is not a chain of one signal to one cell. It is a giant moving web. A single neuron may talk to thousands of other neurons, and each of those may talk to thousands more. There are trillions of connections, and they are not all the same. Scientists have found that brain cells do not speak one language. They speak many. They do not just fire and wait. They send signals in many ways, using dozens of different messengers. And we are only beginning to understand what these messengers do. The most famous brain chemicals are called glutamate and GABA. Glutamate is the excitatory one. It tells cells to fire. GABA is the calming one. It tells cells to slow down. For years, most of our understanding focused on these two. But the brain uses far more than that. More than 100 different chemicals help carry its messages. These are called neurotransmitters and neuromodulators. Some have long names like serotonin, dopamine, and acetylcholine. Others are still being discovered. We do not yet know what they all do, and that is the puzzle. Many medicines that affect the brain do not work on glutamate or GABA. They work on the lesser-known messengers, the mysterious ones, the ones we barely understand. Antidepressants change serotonin levels. Parkinson's drugs increase dopamine. Alzheimer's treatments try to support acetylcholine. These are not the loudest chemicals, but they seem to control much of how we feel and think. Why does the brain use so many chemicals to talk? We are not sure. One idea is that each messenger adds a layer of meaning, like tone of voice in a conversation. Words can be happy or sad or sarcastic depending on tone. Maybe brain signals work the same way. Each chemical may add context, timing, emotion, urgency. That would explain why some messages make you feel calm, others bring anxiety. Some light up memory, others dull your thoughts. But we still do not know how many chemicals are active, or how they interact, or why one chemical has different effects in different parts of the brain. Sometimes the same chemical can act as a messenger in one brain area and a blocker in another. Sometimes it helps one kind of cell but harms another. Sometimes it changes based on time of day, mood, or even diet. This makes brain chemistry very hard to study. What we learn in one experiment may not apply in another. And communication is not just about chemistry. Brain cells also talk through structure. Some signals move across tiny gaps. Others travel through direct contact. Some even pass through long cables that stretch across brain regions. But some messages seem to go even farther, without clear paths, as if carried by invisible waves. We are now exploring the idea that brain cells might broadcast messages like radio signals. These messages may not need direct wiring. They may move in clouds of activity, spreading through space. How is that possible? We do not yet know, but there are signs. In brain scans, we see patterns of activity moving through large regions, too fast to be passed cell by cell. Some think the brain may use electric fields to shape thoughts. Others think waves of chemicals carry meaning across space. And then there is the question of time. Every signal in the brain is fast, very fast. They happen in milliseconds. That is 1,000th of a second. Signals are sent, received, changed, all before you can blink. But timing is not just speed, it is meaning. Imagine someone claps their hands twice, then again, then pauses. That pattern tells you something. It might be applause, it might be a signal. Timing gives rhythm. It shapes what you understand. Brain cells also use timing. They may fire in rhythms, or wait for a pause, or echo each other. The same message, sent at a different moment, can mean something else. The brain may be speaking in patterns we cannot yet decode, And here is where things get strange. Sometimes, brain cells respond to signals we did not even notice. They light up at the same time, across distant areas, as if they are part of a conversation we cannot hear. Maybe they are. Maybe we are missing the code. Maybe we do not yet know what to look for. One idea is that the brain speaks in layers, like an orchestra, strings, horns, drums, all playing at once. Each layer adds to the whole. But if you only hear one instrument, you miss the music. We may be hearing only one layer of the brain's language. And what happens when this language breaks down? That is often when disease appears. In epilepsy, signals fire too often, too fast. In schizophrenia, signals may be noisy or mixed up. In autism, the balance between fast and slow messages may be off. In depression, the mood chemicals may run low. In Alzheimer's, the signal paths may fade away. So many brain problems may begin with broken messages, missed signals, wrong rhythms, lost meaning. That is why understanding brain communication is not just a scientific goal. It is a medical one. It is a human one. Right now we are at the edge of understanding. New tools are helping. We can watch thousands of cells at once. We can tag single molecules. We can see how patterns shift in live brains. But the more we see, the more questions appear. Why does one message bring joy and another bring fear? Why do some cells ignore signals while others respond? Why does timing matter so much? And how do all these messages come together to create a single thought? We do not have the answers yet, but we are listening, more closely than ever. The brain speaks its own language. We are learning the alphabet, one cell at a time, one signal at a time, one discovery at a time, and one day we may understand the whole conversation. Your brain is not silent. It does not sit still, even when you rest, even when you sleep. It is always working, quietly, tirelessly, thought after thought, moment after moment. It takes in sights, sounds, smells, feelings, it sorts them, understands them, makes decisions in fractions of a second. All of this comes from the same soft tissue that looks no more special than a lump of clay. But what happens inside is beyond anything we can truly imagine. At the heart of this mystery lies a question. How does the brain think? Not just react, not just respond, but think, reflect, choose, create. That is what we are trying to understand. It starts with cells, simple ones. They are called neurons. Each one can send and receive tiny pulses. One cell on its own cannot think. But a few billion working together can do something extraordinary. Still, we cannot see that whole process. Not yet. This is what scientists call the movie theater problem. Imagine trying to understand a movie by peeking through a few tiny holes in the screen. You might catch a glimpse of a character, a flash of light, a short burst of sound. But you would miss most of the story. For a long time, that was how we studied the brain. We could only see a few brain cells at a time, a tiny piece of the picture. But the brain does not work in pieces. It works all at once, like a full orchestra playing one grand symphony. Now we have better tools. We can watch thousands of neurons light up. We can track their activity in real time. But even now, we are still only catching parts of the full movie. Billions of cells working together is too much to track all at once. That is what makes this so hard. The brain does not pause to let us study it. It does not explain its steps. It just does the work. And it does it in a way we still do not understand. One of the most amazing things your brain does is recognize patterns, not just once, but instantly, over and over again. You see a face, you know who it is, even in dim light, even if their hair has changed, even if they are older now. You hear a song, and somehow the melody pulls up a memory. Your first school dance, a summer day, a person you have not seen in years. This happens fast, automatically, without you trying. Computers cannot do this as well, not with the same ease, not with the same flexibility. Even powerful machines get confused by small changes. A face turned slightly, a voice with background noise. But your brain handles these changes like nothing at all. It sees the pattern. It fills in the gaps. We still do not know how. Each memory lives in different parts of the brain. Each cell holds only a small piece. But somehow, when you think of someone you love, the whole picture forms. Sight, sound, emotion. all at once, from scattered parts. No one has figured out how this happens. The brain does not have a central processor like a computer. There is no single place that puts it all together. Yet, the brain works as if everything is connected, as if it knows how to pull the pieces into one clear moment. Some scientists believe this happens through rhythms. The brain fires in waves. Groups of neurons pulse together. These waves might help the brain link distant cells into a single thought, like syncing up dancers across a stage. But this is still a theory. We do not yet have all the answers. Another strange power of the brain is its ability to predict. You might think you see the world exactly as it is, but your brain is guessing all the time. It fills in missing pieces. It corrects blurry shapes. It assumes what is likely to happen next. And most of the time, it is right. When you speak with someone, your brain guesses the next word. It hears part of a sentence and fills in the rest. When you walk downstairs, your brain predicts how your feet will land. When something unexpected happens, your brain adjusts in an instant. This is not just reacting, it is predicting, planning, preparing. We do not know exactly how this works, but it happens so fast, you rarely notice it. Scientists believe that your brain builds models of the world. These models are not exact. They are good enough to guide action. They are flexible. They update quickly when things change. This prediction ability helps us survive. It helps us learn. It helps us stay balanced in a world that moves too fast to fully process in real time. And it does all of this using very little energy. That is another puzzle. A computer that plays chess uses huge amounts of power. A brain playing chess uses the same amount of energy as a light bulb. And it is doing much more than just chess. It is also controlling breathing, storing memories, thinking of dinner, feeling love. How does the brain do so much with so little? Maybe the answer lies in how it works differently from machines. Machines follow rules. They do what they are told. The brain seems to work with patterns and predictions and possibilities. It is more like a storyteller than a calculator. It deals in meaning, not just numbers. And that brings us to something truly strange. Creativity. Where does a new idea come from? A song that never existed before. A sentence that has never been said. A story that unfolds in your head. No one knows. The same brain cells that remember what you ate last night can suddenly create a new invention. The same mind that holds old memories can make something brand new. Sometimes ideas appear suddenly, as if from nowhere. A flash of inspiration, a dream, a daydream. You are not trying, but there it is, something new. We cannot track this in the brain, not yet. We know that creativity involves many brain regions, some for memory, some for emotion, some for decision-making. But how these parts come together is still a mystery. Creative thoughts do not follow straight lines. They jump, they twist, they surprise, and the brain seems to like it that way. That might be why boredom often sparks creativity. When the brain is not busy, it starts to wander. It mixes memories, tests ideas, plays with possibilities. We do not understand how it does this, but it is one of the things that makes us human. Close your eyes. Think of your name. Think of the last time you laughed or cried. That voice inside your head, that steady sense of being here, being real, being you, that is consciousness. It is what makes life feel alive. It is not just seeing or hearing or smelling. It is being aware that you are seeing, hearing, and smelling. It is knowing that you are here, in this moment, thinking these thoughts. And yet, for all the wonders science has uncovered, we still do not know how this happens. We call this the hard problem of consciousness, because unlike other mysteries, we cannot touch it. We cannot point to it. We cannot measure it the way we measure blood or bones. We can look at a brain scan and see which parts of the brain light up when you see the color red. But we cannot explain why red feels like red, why it feels warm or urgent or deep, why it does not feel like blue. The brain takes in light waves. It knows how long or short they are. But that data does not explain your experience. It does not explain what it feels like to see something. And that is the heart of the problem. You are not just a body. You are a mind, a person, a self. You wake up every day and carry with you a sense of identity, a quiet awareness that you are still you. You do not have to remind yourself. It just happens. It is there. But how? Your brain is made of cells. Those cells send signals. They exchange chemicals. They create patterns of activity. That much we know. But how does all that activity create a feeling, a thought, a point of view? Some scientists say consciousness is an illusion, that it only seems like something special is happening. But that answer is not enough, because illusions are still experiences. And we are back at the same question. There is another layer to this, a puzzle inside the puzzle. It is called the binding problem. Your brain processes different senses in different areas. Vision happens in the back of the brain, sound in the sides, touch and motion in other places, smell in yet another. But when you look at a tree, you do not see its color in one moment and its sound in another. You see it all at once, a full, rich experience. Somehow your brain takes all those separate pieces and binds them into one single moment. No one knows how it does this. There is no one place in the brain that collects everything, no single cell that sees the full picture, yet the picture is there. You feel it, you live it. This might be the most important thing your brain does. It turns separate signals into one world, a world that feels solid, real, connected. That is consciousness. But it is not all of consciousness, because you are not just aware of the world, you are aware of your awareness. That sounds strange, but think about it. You can notice your thoughts. You can reflect on them. You can say, I am feeling nervous, or I am thinking about my past. You can step back and watch your own mind. That is self-awareness. It is not just reacting to the world. It is watching yourself react. Other animals are conscious too. A dog feels pain. A cat chases light. A bird remembers where it hid food. But humans seem to go a step further. We ask questions. We imagine the future. We worry. We wonder. We know that we know. How does the brain do this? One idea is that the brain builds a model of the world. It makes a kind of map, but it also builds a model of itself, a map of the mind. This allows it to predict not just what will happen outside, but also what will happen inside, how you will feel, how you will act. And this creates the sense of being a person. That model might be what we call me, but again, this is still just a theory. There is no single me center in the brain. Just as there is no one place where all your thoughts come together. It may be the result of many parts working in harmony, or it may be something we have not yet discovered. Another clue lies in attention. Your brain is always busy. It processes millions of bits of information every second, but you're only aware of a few of them. Right now, you are reading these words. Maybe you are also hearing a clock or feeling your seat, but you are not paying attention to all of it at once. You cannot. Consciousness has limits. It is like a spotlight on a dark stage. Only one thing can be in the light at a time. The rest is still there, but hidden. What decides what comes into the spotlight? What stays in the dark? This is another mystery. Some scientists think attention is the key to consciousness, that what you pay attention to becomes part of your experience. Others think attention is just one piece of a bigger puzzle. We do know that attention can shift, that you can choose to focus, or your brain can pull your focus for you. A loud noise, a sudden thought, a strong emotion, they can all grab the spotlight. And as the spotlight moves, your experience changes. But no one knows what controls the light, or how it links to your sense of self. There have been strange cases that add more questions. People with brain injuries who lose part of their awareness. They may not know one side of their body exists, or they may speak without knowing they are speaking, or act without remembering they did. These cases show us that consciousness can break, that it is not all or nothing, that it comes in pieces, and somehow, when all the pieces are together, the feeling of I am appears. It is not magic, but it is not fully explained by science yet. Even dreams add to the riddle. In a dream, you feel things, see things, believe things, but none of it is real. Still, it feels real. You are conscious, but in a different way. What changes in the brain to make this happen? Why does your sense of self stay, even when the world around you is imaginary? We are still trying to understand this. Some say consciousness is a product of complexity, that when a system becomes complex enough, awareness emerges. Others say it comes from special patterns, or from information flowing in just the right way. Still others believe we may never fully understand it, that the brain may be too complex to fully know itself. But that does not mean we should stop trying. Consciousness is not just a scientific question, it is a human one. It touches everything we care about. Love, fear, hope, meaning, morality, art. All of it begins in awareness. To understand consciousness is to understand what it means to be alive. So we keep searching, bit by bit, cell by cell, idea by idea. And maybe someday, we will finally understand how a quiet lump of cells can create the voice that says, I am. Think back to your first day of school. Try to picture it. Maybe you see your shoes, your teacher's smile, the sound of laughter down the hall. You feel it like it was yesterday, but it wasn't. That day happened years ago, and yet somehow that moment is still with you. Now think of what you had for lunch 2 weeks ago, or what you wore last Tuesday. Maybe nothing comes to mind. That memory is gone, or buried so deep you cannot reach it. This is the mystery of memory. Why do some moments stay and others vanish? Why does a random smell bring back something from childhood, while something that happened this morning fades before dinner? Where are these memories kept? And how does the brain choose what stays and what goes? We live our lives collecting moments, but we do not know where they all go. Your brain stores everything that makes you who you are. Your name, your family, your fears, your favorite song. But the brain is not a filing cabinet. It has no folders, no drawers, no address where each memory lives. If a computer needs to store something, it saves it in a specific spot. It can go back and find it anytime. The brain does not work that way. Scientists have searched for years to find where memories are stored. They thought there might be one place, one center that holds everything. Then they thought maybe memories are spread out, pieces here, pieces there. Now they believe it is both. Memories are made across the brain. Different types of memories live in different areas, but even that is not the full story. One part of the brain, called the hippocampus, plays a big role. It is shaped like a seahorse. It helps turn short-term memories into long-term ones. But once a memory is stored, it may move, it may spread, it may settle into the outer parts of the brain, into networks, not one single spot. This makes memory hard to pin down. You can lose one part of the brain and still remember who you are. But if damage spreads, memories start to fade. With Alzheimer's disease, people begin to forget their history. First small things, then big ones, names, faces, relationships. The brain cells holding those connections begin to die, but even this shows how much we still do not know. We can see brain areas change, but we cannot say for sure which cell holds which memory. If you remember your 10th birthday, we cannot point to the exact place in your brain that stores it. This is the storage problem. It gets stranger. Because memory is not just about storage, it is also about making. Each moment we live could become a memory, but most do not. You see thousands of faces, but remember only a few. You hear hundreds of voices, but only some stick. Why? The brain seems to decide. It holds on to things that matter. But what counts as important? Sometimes we remember what scared us, or what surprised us. Sometimes we remember things that seemed small at the time. We do not choose what stays. The brain does, and no one knows the full list of rules it uses. We do know that strong emotions help. Joy, fear, sadness, these leave deeper marks. They activate brain chemicals that help lock in memories. That is why you remember your first heartbreak, or the moment you won something, or the day you lost someone. But that is not always true. Trauma can erase memory too. The brain can hide it or blur it. Sometimes the memory is too sharp. Sometimes it is completely gone. There is more. When you recall a memory, you are not playing back a recording. You are rebuilding it, bit by bit. Each time you remember something, your brain pulls together the pieces. It uses parts of vision, parts of hearing, parts of feeling, and it stitches them into a picture. But here's the twist. Every time you remember, you can change it, slightly, without meaning to. A detail shifts, a word changes, a color fades, and the brain saves the new version. Memory is not fixed, it is alive. This can be a gift or a danger, because the brain can create memories of things that never happened. They feel real, they have detail, emotion, shape, but they are false. They may come from dreams or stories or guesses, and still they feel true. You can remember being somewhere you never went, saying something you never said, seeing someone you never met, and you will believe it with your whole heart. This is the false memory puzzle. It has been tested in studies. People were shown fake photos of events that never happened. Later, many said they remembered those events. They filled in details. They added color. Their minds created the memory from suggestion. This shows how delicate memory is. It shows that confidence does not equal truth. You can be sure and still be wrong, and that brings us to forgetting. We often think of forgetting as a failure, but it may be a feature, a tool the brain uses on purpose. After all, if you remembered every single thing, you might drown in information, every word, every step, every passing face. You would be buried in noise. Forgetting clears space. It sharpens focus. It helps you make sense of the present by letting go of the clutter. But how does the brain decide what to forget? We do not know. It may remove memories that are no longer useful. It may hide things that are painful. It may keep the strongest memories and fade the rest. There are even cells in the brain that seem built for forgetting. They trim connections. They erase old links. They keep the brain flexible, ready to grow, ready to adapt. Memory and forgetting work together. Like two sides of a coin. You need both to live well. Some scientists think we might one day help people remember better, or forget better. Imagine helping someone with memory loss recover the past. Imagine helping someone with trauma forget the pain. We are just beginning to understand how that might work. Some researchers are trying to map the memory cells, to see them fire, to watch them grow and shrink. Some are testing ways to control memory with light. Others are exploring how sleep helps store memories, how dreams may sort the important from the unimportant. This is the frontier, a deep maze with many doors. Memory is not just a storage system, it is a mirror. It shows you who you are, your past, your choices, your voice. It lets you tell your story. It connects you to the people you love. It gives you meaning. And the more we learn, the more we realize how precious it is. We are made of memories, and every day we make more. Every night we disappear, not in body but in mind. We lie down, close our eyes, and drift into something we cannot control. Sleep takes us. Thought slows, awareness fades. We slip into silence, and we do this every single day of our lives. We spend almost a third of our time asleep. If you live to 80, that means you will have spent more than 25 years not awake, just sleeping. But why? That is the mystery. All animals sleep. Dogs, birds, whales, insects, even creatures with tiny brains rest. Sleep is built into life, yet no one knows exactly why. We know what happens when we don't sleep. It starts with yawning, slow thinking. Then the body stumbles, memory fails, emotions grow sharp. With enough time, the mind begins to break. Hallucinations, panic, confusion. And if you keep pushing, your body begins to fail too. In extreme cases, lack of sleep can even lead to death. This shows how important sleep is. But it also shows how strange it is. Because when you sleep, your muscles go still. Your awareness turns off. You become helpless. In nature, that is dangerous. Yet evolution has kept sleep in every species, which must mean one thing. Sleep does something we cannot live without. But what? For years, scientists believed sleep was simply rest, time for the body to recover, to save energy. But the brain does not rest during sleep. In fact, parts of it become even more active. Your heart rate changes, your breathing slows, but your brain lights up. It works quietly behind closed doors, as if the night is its time to clean, fix, and sort. One of the strongest ideas is the memory cleanup theory. During the day, your brain takes in a flood of information. Sights, sounds, emotions, facts, names. It is too much to hold on to. So at night, your brain may go through it all and decide what stays. Scientists believe that during sleep, the brain replays certain patterns. The same patterns that happen during the day, like a rehearsal, a soft echo. This may be how memories are made stronger. Some things get saved, others get wiped away. This would explain why sleep helps learning. Students who sleep after studying do better. Athletes who sleep well perform better. Even babies learn faster when they nap. It also fits with brain scans. During sleep, we see activity in memory areas like the hippocampus, like the cortex, as if the brain is filing away the day. But we still do not know how it decides what to keep or what to let go, and memory is only one part of the sleep story, because not all sleep is the same. We move through stages: light sleep, deep sleep, and REM sleep. REM stands for rapid eye movement. This is when dreams happen, and it may be the strangest state the brain enters. In REM sleep, the body goes still. You cannot move, but the brain comes alive. It creates scenes, stories, worlds. You are the main character. You feel, you act, you believe. Sometimes your dreams are strange. Sometimes they make perfect sense. Sometimes you remember them. Sometimes you don't. But inside a dream, it feels real. That is the dream puzzle. Why would the brain bother with this? Why does it create full experiences while you are asleep? Why do they often include people, places, or fears from real life? Why do some dreams teach while others confuse? We do not know. Some believe dreams are practice, a way to rehearse danger, to prepare for problems. Others say dreams help with emotion. They let the brain process pain or joy without risk. Some think dreams are just side effects, a result of brain noise, but none of these answers feel complete. Because dreams are too detailed, too rich, too important to the dreamer. They affect us, they stay with us. A dream can shape your day, even your life. And here's the twist. Some people know they are dreaming. In the middle of a dream, they become aware. This is called lucid dreaming. It shows that the brain can be partly awake and asleep at the same time. That leads us to the next mystery. How does the brain turn consciousness off and on? You do not flip a switch to sleep. It happens naturally. Slowly. Your mind drifts. You stop thinking clearly. You stop noticing your thoughts. Then, nothing. When you wake up, the opposite happens. In a second, the world returns. Your name, your room, your sense of self. It was always there, just hidden. But how? Which part of the brain turns awareness on? What holds the key to the self? Scientists are still searching. They look at brain waves, at activity levels, at chemicals that change during sleep. They know some areas control wakefulness, like the brainstem, like the hypothalamus. But no single area has been found that holds consciousness. It may be spread across networks, a pattern of activity, a certain balance. When the balance shifts, awareness fades. When it returns, you wake. But even in sleep, not all awareness is gone. People can hear their names, respond to alarms, sense danger. Some people talk, some walk, some solve problems, all while asleep. This means the brain does not fully shut down. It shifts modes, like switching programs, one for the day, one for the night, one for dreaming, each with its own rules. And yet you are always you. That is the most powerful part of this puzzle. That through all these changes, through silence and sleep and dreams, your sense of self stays. Even when it hides, it comes back. You are not aware during deep sleep, but when you wake, you remember being you. That thread remains, unbroken. Some scientists believe this thread is what matters most, that sleep helps protect the self, by giving the brain time to restore, to balance, to reset. Without sleep, the self begins to blur. Thoughts break apart. Emotion runs wild. Memory slips. Sleep may be what keeps the self together. Still, we have much to learn. We do not yet understand how dreams are chosen, why nightmares happen, why some people sleep deeply while others wake often, why babies sleep so much, why older people sleep less, what sleep does in the long run. We know sleep helps the body heal. We know it helps the brain grow. We know it affects mood, weight, heart, and mind. But the full story is still unfolding. Sleep is not wasted time. It is not just rest. It is an active, vital state, a second life, a secret world your brain enters every night. It is where learning deepens, where memories settle, where the mind finds peace, where your private theater plays scenes that only you can see. And it all happens without your permission, without effort. You close your eyes, and the brain takes over. It has done this every night since you were born. It will keep doing it for the rest of your life. And every time you wake up, you return to yourself. You know what it feels like. A rush in your chest, a knot in your stomach, a quiet joy rising behind your eyes, the warmth of pride, the sting of shame. Emotions shape every moment. They arrive without warning. They shift the way we see the world. But where do they come from? We feel emotions deep in our bones, but they do not just happen to us. They are made, created by the brain, formed from signals and patterns and responses. That is the first truth. The brain is the engine behind every feeling. It watches what is happening. It gathers clues. It compares them to past moments. Then it reacts. And that reaction is what we call emotion. But this is not something we control. You might cry when you do not want to. You might feel anger when you wish you could stay calm. You might laugh in the wrong place. You do not choose these things. Your brain does. And here is the mystery. The same moment can make different people feel completely different things. One person sees a dog and feels love. Another feels fear. One child speaks on stage and feels proud. Another trembles. The outside world is the same, but the emotion changes. Why? We do not yet fully know. Each brain builds emotion using its own map. That map comes from memory, from body chemistry, from life experience, from personality. But no two maps are the same. And so, emotion is personal, deeply personal. Scientists have tried to predict emotions. They have studied faces, heart rates, brain scans, but it is hard. Emotions do not follow one simple pattern. They are not like a light switch. They are more like a storm, shaped by many winds at once. And those winds often start in the body. That is the second truth. Your body and brain are always talking. A feeling in your chest, a flutter in your stomach, tight shoulders, warm cheeks. These are not just side effects. They are part of the emotion. In fact, sometimes the body feels something first. Your heart might race before you realize you are afraid. Your muscles might tighten before you know you are angry. The body sends signals. The brain listens. It pieces the clues together. Then it gives you the emotion. This back and forth makes emotion hard to study. It does not live in one place. It lives in the loop between your brain and your body, and every emotion you feel is shaped by this loop. You might think fear lives in the brain, and it does, but it also lives in your breathing, in your hands, in your gut. That is why emotions can feel so physical. They are not just thoughts. They are full body experiences. That is also why calming the body can calm the mind. A deep breath, a walk, a hug. These things speak to both the body and the brain. But there is more. Some memories stay with us forever. The moment you got hurt. The time someone said something kind. The day you fell in love. These memories are different. They feel stronger, more vivid, more real. That is the third truth. Emotion makes memory powerful. When something matters to you, your brain takes notice. It marks the moment. It holds on tight. It stores it in a special way. This is not just a feeling. It is biology. Brain scans show that emotional memories activate areas like the amygdala and hippocampus. These parts help store memories, but they also respond to emotion. When both are active together, memories stick. This makes sense. Strong feelings signal that something is important, so the brain saves those moments, just in case it needs to remember them later. That is why people with trauma remember things in great detail, and it is why happy memories can feel like they happened yesterday. But this power can also confuse us. Sometimes a memory feels strong not because it is true, but because it was emotional. Emotion shapes how we remember. It colors the past. It makes us sure, even when our memory is off. And this leads to a deeper question. Why do we even have emotions? What is the point of feeling shame? The answer may lie in the people around us. That is the fourth truth. Emotions are not just personal. They are social. Humans are not built to live alone. We depend on each other for safety, for comfort, for meaning, and emotions help us live together. Think about it. Shame happens when we break a rule. Guilt happens when we hurt someone. Pride comes when we do something good and others see it. Embarrassment comes when we are seen in a way we do not like. These feelings only make sense if other people are there. This means the brain is watching not just what is happening inside you, but also how others see you. Your emotions guide your place in the group. Scientists believe this ability to feel social emotions helped us survive. Groups with strong emotional bonds worked better together. They shared more, protected each other, passed on their genes, so our brains evolved to care what others think. That is why approval feels so good, and rejection hurts so much. Some of these emotions begin early. Even babies show signs of pride and guilt. Others grow with age, as we learn what matters to our family, to our culture, to our friends. These emotions are learned, but they are also deeply human, and they raise hard questions. What happens when emotions grow too strong? What happens when they go missing? What if the emotion does not match the moment? These are the questions behind mental health. In depression, sadness becomes heavy. It sticks. It does not follow reason. In anxiety, fear rises without cause. In some conditions, emotions go flat. A person feels nothing, not joy, not sorrow. These are not choices. They are changes in the brain and body, and they show us how powerful emotions are. They shape our decisions, our relationships, our identity. They tell us what matters, what is safe, what is good, and what hurts. Without emotion, life would be flat. Facts without meaning, days without color. We need emotion to care, to connect, to love. But understanding emotions is hard. They are made in many places. They rise from many signals. They change from person to person, and they never sit still. Still, we are learning. We now know more about the chemicals that help shape emotion, like serotonin, dopamine, oxytocin. We know more about the brain regions that help track and respond, like the amygdala, the insula, the prefrontal cortex. We are building maps of emotion, maps that help us treat emotional disorders, that help us understand what happens in sadness, in rage, in joy. But emotion is not just chemistry, it is experience. It is shaped by your story, by your culture, by the people who raised you, by the things you've survived. That is what makes emotion so human. And that is why it remains one of the greatest mysteries of the brain.